in the electric fields, practice problems, number 1, it says, it gives you like a fixed point charge. Is that right?
Imagine a fixed charge of Coulomb.
Okay. Okay, so let's say that, so this is +1 coulombs, and the coordinate system, well, that won't really matter. And let's think about a few points and use Coulomb's law to figure out what the force is and what we know about the directions. So, okay, let's first imagine like a set of points that are a distance of 0.1 meters from the charge. Okay. Coulomb's law says the force, and what are we supposed to draw? Electric field vectors? Or the electric field lines? Okay, so remember that to calculate electric field vectors, you can do that by calculating the force vector on a 1 Coulomb test charge. Okay, so I'm going to calculate E this way. 8.988 times 10 to the 9 times the charge of the, the fixed charge times our test charge, and I'm going to use +1. You really could use any test charge, but then you'd have to divide by it at the end, And then the distance that we chose was 0.1, so this is going to be 0.1 squared. And so you get 8.988 times 10 to the 9th divided by 0.01, which is the same thing as times 100. So you end up with 8.988 times 10 to the 11th. And what are the units of the electric field vector? It's based on, think of, so electric field vector is force vector divided by Q. So it's going to be newtons divided by coulombs. Okay, so this is newtons per coulomb. And if these are both positive, I chose a +1 test charge. What direction is that electric field vector going to point? Towards or away? Away. So these would all be, the length I'm making these is arbitrary, but they would all be the same length, and wherever you are, they'd be pointing away. That's right. And so when you're trying to calculate these for, when you're trying to calculate these electric field vectors, just think of calculating a force with a test charge of +1.
Always?
Yeah, that's always the way to do it. Yep.
So there will never be like a negative where it's pointing?
Well, if you're asked for the force vector, then you have to know what the test charge is. But you can be asked for the electric field vector without being told anything about a test charge. So then just use a test charge of +1. Yep. And calculate the force. Okay, so now second, let's say we have 1 meter from that fixed charge. Then the electric field vector magnitude is 8.988 times 10 to the 9 times 1 times 1, those are the charges, and then divided by 1 squared. So you get a magnitude of 8.988 times 10 to the 9 newtons per coulomb. So that is 1/100th of the length of this. So say say these are all the points that are 1 meter away. Okay, then those forces are this way, this way, this way. Okay, and so, yep.
For us to do this problem on our own, we could have just made any length, right? This is just an example, and you're using 1 meter and 0.1 meter.
Oh, yeah, right, exactly. You can use any location, any distance. I guess I just chose 2 different distances to do it kind of at, I don't know. So you could see just how the magnitude changed as you got farther away. But yeah, you could, those are just totally arbitrary distances. But now, maybe you can see that if you wanted to draw field lines that are parallel to these everywhere, those field lines would just go like this. They'd just be straight lines going away. And actually, maybe you just remember that too for the field lines for a fixed charge. So the blue are the field lines. And now the equipotential lines, well, I've already drawn these 2 circles. The green and red circles are equipotential lines.
And the field lines are basically where the points are pointing away towards, right?
The what?
Where the points are, where the, I mean, going out, where on the side.
Those are the field lines. Yep. So the red and green are equipotential lines. And now we have to figure out which one is a higher electric potential and which one's a lower one. I think they asked that. They is me, by the way. I'm not trying to pass the buck. The voices in my head. Okay, so who has a strategy for figuring out whether the green or the red is the higher electric potential?
Well, I thought it was closer. It's going to be at the higher electric potential.
Well, so the way to think about it is, again, think about it as potential energy for a +1 Coulomb test charge. Okay, so where is this force trying to get a +1 Coulomb test charge? Far away, right? And it doesn't want it close. Okay, so that's for a +1 Coulomb test charge. So +1 Coulomb test charge is going to have a higher potential energy close and a smaller one far away, because potential energy always tries to get things to a lower potential energy. So these forces, they're trying to force a +1 Coulomb test charge to go away. That means that away is lower. Yeah, you could just calculate it too. That's true. Yep. Was that asked for in the problem?
Sort of.
So yeah, you could calculate it too.
You can calculate the electric potentials on an equipotential line to determine where the.
Yeah, right. Okay, so yeah, that's a good way to do it too. So at 0.1 meters away, the electric potential is equal to 8.988 times 10 to the 9 times the fixed charge divided by R, and so you get 8.988 times 10 to the 10, and what are the units? There's something here that gives you a really good hint. Electric potential is always volts. And at 1 meter, you got 8.988 times 10 to the 9 times the fixed charge divided by the distance, 1, and so you get 8.988 times 10 to the 9 volts. And so if you're closer, the electric potential is higher. If you're farther away, the electric potential is lower.
That's not the same thing that you did on the other one?
When I just sort of explained what was happening, well, this was a calculation and the other one was just thinking about what how potential energy relates to the direction the force is pushing something.
I guess the question I'm asking is, up above, we figured out the charge at a given point, correct?
Up above here?
Yes.
So we figured out the magnitude of the electric field vector, which is, remember, that's this thing. So we figured out the force vector divided by the test charge. But now we're talking about energy stuff. These equations, they look so similar, it can be confusing. But remember, the electric field vector is related to force, and the electric potential is related to potential energy.
So the volts, the V,
Mm-hmm.
so it's still basically the force vector divided by.
So V is the potential energy divided by the test charge, yep. And E is the force vector divided by the test charge. Do you want me to give you another one sort of like that and you can work through it?
Yeah, and then one for dynamics.
Okay, yep. So let's say you have a fixed charge of a single electron. So first, calculate electric field vectors at, let's say, 4 locations. Use part A to sketch the field lines. Use part B to sketch the equipotential lines. And which equipotential line has greater and smaller electric potential. Okay, so see if you can work through that.